Okay, 6.6 is operations with vectors in R squared. So this is just two-dimensional space, just an x and y coordinate. So the first thing we need to understand in this section is what a position vector is, because wherever a vector is in space, we like to position it with this tail on the origin. So a position vector, we usually call it OP because one of its points is at the origin, the other point is at some random point P, has its head at that point, that could be AB, and tail at the origin, 0, 0. Which means that any vector can be written as a sum of two components. So for instance, if this is AB, then we know this already, that the vertical distance here is just going to be the y value, B, times the direction of this component. And we know the vertical component, we can multiply it by the unit vector, J. Because J is a unit 1. Let's say J is right here. It's a unit 1. If we multiply it by B, we scale it to the same scale as whatever the component of B is. And likewise over here, we call the x component I, vector I. So the whole thing is I scaled up to A. So this is AI. Okay, now we have two components based on the scales of P, and we can rewrite a vector OP, if it equals like an algebraic coordinate, as this. Okay, and we use these unit vectors to understand just like the direction, right? This is just horizontal, this is just vertical, and then eventually we're going to get the z value too when we do 6.7. So here's a quick example. If we're given vector A is a position vector OA, and it's at 1, 3, and we know B is 4, negative 2, determine the components of A plus B and A minus B. So I'm just going to write A plus B over here, A minus B. But I'm just going to draw some things to show you where things are at. So for instance, A is 1, negative 3, and B is down here somewhere. B is 4, negative 2, and they all come from the origin. All right. Now, A minus B and A plus B, so if I did my parallelogram over here, this is going to be my A plus B. But we don't even have to understand it this way, because if we're adding components, like look at the horizontal component of A, like just the x value, and then look at the horizontal component of B. All we have to do is just add up those components, and we know that the orange one, A plus B, has to be a sum of those components. So I can go over here and just say, well, I know this is 1, 3. I know this is 4, negative 2. So A plus B is just 5, 1. And that's actually where this point is. This is at 5, 1. And we can call this whatever, P. Doesn't really matter. It's the end of A plus B. And it's also a position vector, right? OP we can call it. Over here, A minus B, take a look what happens here. So we're going to do 1, 3 minus 4, negative 2. And we're going to get negative 3 and 5. So look where negative 3, 5 is. It's negative 3, 5. It's over here somewhere, right? This is my A minus B. This is the same vector, I know it's not the scale, as A minus B over here. Should be the same size, sorry. Okay, but we don't like its tail not at the origin. So what we do, when we subtract, we actually shift it to have its tail at the origin. And now it's the same vector, it's parallel, it's the same magnitude, just its tail is at the origin, and we have it, with its head at that point, negative 3, 5. Okay, so adding and subtracting vectors algebraically is like extremely simple. Okay, let's move on to a few other examples. Okay, the next few examples, pretty important, pretty easy though, but just subtle differences like the magnitude of AB plus BC versus the magnitude of AB plus the magnitude of BC. So simple things like this can cause mistakes, clear up some confusions. So we got two vectors in space, in our space, our squared space rather. We want to calculate these two things. We know the values of A, we know the values of B, they're 2 points in space. So to do AB plus BC, first of all, I definitely need a C. So I'm going to write a C down over here, and we're going to call it 8, 18. Okay, so I'm going to find AB over here. Let's go with pink. And to find AB, I just have to subtract. If these are the 2 points, then the horizontal distance between AB is just a subtraction, right? It's the distance in X. And likewise, it's like the slope. It's like rise over run, just not rise over run. You just have to subtract the 2 points. So AB is going to be 5 minus -3. That's not a comma. And then 22 minus 7. 5 minus -3, 22 minus 7. So vector AB, I can say now is 8 and 15. Okay, and I finally have vector AB. Okay, and I'm going to do the same thing with BC without showing the work. And I should get 3, -4. Okay, just subtract. Yeah, okay. So now I can actually do AB plus BC. So let's go with a different color. I'm probably gonna run out of space here. I'm gonna do AB plus BC like we did on the last slide, or whatever you want to call it. We're gonna do this 8, 15 plus 3, -4. So the vector AB plus BC is 11 and 11. This is AB plus BC. But this is the magnitude of that vector. So the magnitude of this, what a horrible color, is like the distance from the origin to this point, which is just 11 squared plus 11 squared in here. And that's going to be 2 times 121. And the root of that, let me just check, a little cheat. Can't find it. 15.6, 15.56. Okay, just find the square root, leave it as a simplified root, whatever you want to do. But that is the magnitude. After I find the position vector, I then use distance. Really, really easy. This one, on the other hand, okay, I'm done orange, get out of here. This one, on the other hand, first I have to find the magnitude of AB, then I gotta find the magnitude of BC. So the first thing I'm gonna do is find the magnitude of AB, and that's just gonna be 8 squared plus 15 squared. I'm gonna find the magnitude of BC. Now, the book does, uses negatives for magnitude. I never do. Doesn't make any sense. If you're squaring a negative, it's gonna be positive, so stop writing the negative. So this is gonna come out to be 17, and BC is gonna be 5. Now that I know the magnitude of AB and the magnitude of BC, I can now say that the magnitude of AB plus the magnitude of BC is just 17 plus 5. 17 plus 5. 22. Okay? They're different. Of course they are. Okay, but just, subtle differences in notation. We're kind of new to vectors. Could cause errors. So be careful. Magnitude is like the easiest thing ever. Just square numbers, add them, square root them. It can't get easier than that. It's a complete joke. Okay, last question. We have vector A, B, and C, and we want to calculate the magnitude of all these scales applied to these vectors. Okay, it's not really a problem. This means that 5, -6 minus 3 times vector B. So take a look at how I'm multiplying the scalar here. Minus half of 2, 8. It's just like grade 9 distributive property. So this is going to turn into a 5, -6. I'm going to add and throw that negative on the inside by my choice. I'm going to add and throw that -half on the inside. And now I got rid of my scales. And now I'm just doing vector addition. I can separate them into components, and I can say 5 plus 21 minus 1 is 25. And I can say negative 6 minus 9 is negative 15, negative 19. Now, this is just a minus 3b minus half c. That's what that equals. To find the magnitude, I now have to just do 25 squared plus 19 squared and square root that. That's it. And this comes out to 31.4. And this is going to be the magnitude of this with the absolute value. Okay, so just understanding the difference in magnitude versus, the actual vector is a pretty big deal when you first start this. And that's pretty much it for 6.6. Pretty easy.